Okay, so in the last class, we discussed the effect of variation on SRAMs, specifically intra-die and inter-die variation, and talked about how critical it is to come up with ways to counter this variation, counter the effect of variation, right? There will always be variation. There is no getting away from it. We just have to accept that and design something in the circuit level or system level to make sure our systems still work. And we looked at one approach towards achieving something like that. This is definitely not the only approach. And the reason why it's published is because most probably industry is not using exactly this approach at this point. But that tells you that there are ways you could counter this variation. And maybe you could think about something even smarter than this, right? Even more efficient than this. In going through this process, we had to learn a few things. The number one take-home message was you can modulate the properties of a transistor by changing its body bias, right? And effectively, you can change its threshold voltage. So this is a concept that will probably help you in a lot of your circuit designs moving forward. So in the next slide, where we will begin today, we only have a couple of slides left here in this lecture. And then after that, I'll start a new lecture. And before I start, I'll give you a few messages. So let's get it done first. Now, inter-die variation and cell failures. What do I mean by cell failures? When you try to read from an SRAM cell or write into this SRAM cell, if you fail to do so, that's failure, simply. And even if you have one kind of failure, be it read, write, or hold, you try to do something, you couldn't. That's the failure. So you see, there are many ways a memory could fail. That means there is a higher likelihood in terms of probability that you have an overall failure. One other thing is, we have to keep in mind, as I'll show you in the next slide, there is a difference between cell failure probability and memory failure probability, and we'll talk about it soon enough. When I say cell, memory cell is just one of the SRAM 6 transistor combination, right? That basically stores one bit. When I say memory, it's the entire array, right? So notice it's more probable for the memory to fail than the cell to fail, because maybe one cell will not fail, maybe the other one will. So you have billions of cells. Even if one of them fail, your memory failed. Notice that's why it's so easy for the memory to fail than a cell to fail. We'll get there. So this is the distribution of a parameter maybe, and typically the most important parameter is the threshold voltage. So we are just portraying the VT shift here, threshold voltage shift. What it shows you is that this is the nominal value, and on your right, you have higher threshold voltage. On your left, you have lower threshold voltage, right? So there will be both kinds of variation across your array. Now, look at this side on the right, where you have higher threshold voltage. Higher threshold voltage makes your transistors weaker, okay? And notice there is a higher probability of excess failure and write failure. Why is that? Because remember, during write operation or excess, you have to make sure your excess transistors are capable enough to interact with the internal cross-couple inverters. Now, high VT makes them weaker. So it acts against what you need. So there is a higher probability of failure in this region. Am I making sense? Okay, there are ways you could have failures on the other side as well. Maybe when you make the threshold voltage lower, your excess transistors become strong, for sure. But then you have other challenges. Now they might become too strong to have read failure and hold failure, right? So there is no ease in either side of the spectrum, basically. Here or there, doesn't matter. So you have to account for both kinds of variation that's leading to any kind of change in the threshold voltage. So keeping that in mind, let's see some realistic data. This is a plot from, obviously, as you can see, this is a realistic diagram that shows actual numbers. This is failure probability. Notice 10 raised to 0 represent 1. What is 1 in terms of probability? 1 represents 100%. You know that? You cannot have a probability more than 1. So that's why there is nothing above 1, right? If there is 1, that's really, really bad news, meaning this is definitely going to fail, okay? You don't want that. So the lower you can get, the better it is in terms of usability of a memory system, right? So I don't have to tell you, the only reason that is usable would be which one? Region. So there are 3 regions, region A, region B, region C. Region A and C has they will both have issues because there is 100% failure probability, which shows, by the way, why is that the case? What is there in the x-axis? That's the VT shift or threshold voltage shift. Zero shift means you get what you designed it for. Like you assume that you get 0.2 volt as threshold voltage, you're gonna get 0.2 volt, which is very unlikely. But if that is the case, no chances of failure because they have designed everything considering that. And then up to a certain range in both directions, you have a very low chance of memory failure. You see that? But the chances of cell failure is higher, still much less than 1, much less than 1. And notice, this is orders of magnitude. What is 10 raised to minus 5? 0.000 blah, 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 1, right? Several zeros and 1, as you see. So that's way less than 1%. So this is good. So you have designed it well. The closer you get to 1, the worse this thing becomes. So by design, we make sure that there is a region within which there is a lower cell failure probability. And for the array, the failure probability is even lower than that. And I'll explain the situation in a second. Yes. Yes. Great question. Yes, these are all taken for one particular VDD, supply voltage. The moment you change the supply voltage, things will change. Things will shift as well. So once we design something, we always design it based on a supply voltage. Because you know what? The supply voltage is determined by the overall system. So if your processor is working with a particular supply source, that's what you have, basically, right? So that's a good point. Yes. But if you change VDD, that will definitely change. Yes, I'll explain that. So imagine in a memory array, you have billions of cells, right? As I told you, like when you have rows and columns, each of these crossover points would be a cell. But this entire array is the memory, right? So when I say cell failure, that's the probability of one of them failing. But notice, maybe this one is too good. It's not going to fail. Maybe the other one will. So for a particular cell, the failure probability could be lower or higher. But for array, it's a different story. Even if one of the cell fails or a good amount of cell fails, the memory will fail. And there is a little bit of complexity that I haven't explained yet. Let me clarify that first. So in the memory array level, we always use a lot of redundancy. For example, we know that there could be degradation, there could be failure in some cells, and there are ways to detect failure. There are ways to detect whether a cell is stuck at a certain. There are different kinds of failure. Stuck at 1 failure, stuck at 0 failure, meaning a cell is programmed to be 1 all the time. No matter what you try, it never changes. So there are algorithms that people use. These are all architecture and algorithm level innovation, by the way. Okay, they keep checking whether things are working perfectly or not. You cannot just believe that everything will work, right? You have to keep checking. There has to be checks and balances. And many of these come from the architecture and system level. And we always keep some redundant rows in most memories to make sure that we could account for if a row appears to be malfunctioning, you could change it to a redundant row. There you go. You will assume that this row doesn't exist anymore. Am I making sense? So those redundancies make sure that your memory failure probability is much less. Even if a few cells fail, they can fail, of course. The memory will probably not fail that easily. Am I making sense? So that's by design, because of redundancy, because of other error correction techniques. There are even error correction codes. There are parity checking approaches that people like. Every time you do some sort of cross checking, you make sure that the data is okay. It's not really corrupt, right? There are very easier checks that people do. That's called parity check. For example, you just see whether the number of ones that you are expecting in the data stream is the same as what you're getting. It's very rudimentary check. It doesn't tell you exactly where the error is, but it tells you that there is an error in this chunk of data. And then you narrow it down within that chunk and figure out the cell that's not working. And maybe you change the entire row. Maybe you change a block. So all of these are architecture level decisions that people take, which we're not getting into the details of in this course. Am I making sense? Okay. So, but the point is there is a range of VT shift that your design can take, beyond which there will be different kinds of failure. And this is, like I said, this is a realistic data. It shows F represents access failure. WF represents write failure. Remember, as I told you here, if you have higher VT, you have access failure and write failure. Okay, because your access transistor becomes weak. Here you have read failure and hold failure. Meaning, even when you are not reading or writing, spontaneously, there is a chance that the data will flip or degrade, okay? Because your access transistors are too strong, right? They will interfere with the storage node. Are you guys all with me so far? Okay, by the way, these are all interesting questions. And you don't have to memorize, obviously. You cannot remember this, but you have to logically think. Oftentimes, there will be questions. I mean, I'm giving you a hint here. Maybe in your midterm, there could be a multiple choice question or a true-false question. And I ask you, okay, what kind of failure can you expect here in this region? And if you say right failure, that's not right, really, because you are looking at a lower threshold voltage, which makes your access transistor really strong. There is no chance that you'll have a right failure. Making sense? Okay. All right. And this is the nominal VT region where you want to operate. So notice every design has its limit. As an engineer, you have to make sure that you make your system work within the limit that your company wants it to operate in. And beyond that, you have no way to ensure things will work. There will always be breakdown beyond a certain threshold. Okay, that brings us to the close of this particular lecture. And I uploaded 2 lecture slides you might have noticed on Canvas, slide number 5 and 6. I will start with 6. Here is why. Slide number 5 talks about HSpice tutorial. So in the last time when I taught this course, I went through a live coding in class. And we ran into issues like, oh, somebody is stuck with laptop issues, somebody is not being able to access the server, this and that, right? So it was in a 50 minutes class. It was really difficult to kind of handle all of this and have some meaningful progress. And eventually, when we, got done, it took like several classes to get through the tutorial, and it was very confusing for everybody. So I decided against it. What I'm gonna do is I will create a coherent, continuous tutorial in a recording format, and I'll share it with you. It's like one of those cooking videos that you watch on YouTube. So you have to go over this on your own at home whenever you find the time, weekend, whenever works. But do go through them. I'll try to be as detailed as possible. And then I will open up questions, or maybe if you want a dedicated session, I'm more than happy to do so. But I want you guys to go through this on your own first to get yourself familiarized with HSpice. Okay, and then that's what I'm gonna share after this class. Maybe not today, maybe tomorrow or before the end of the week. Okay, I'm kind of finalizing the recording and everything. It's probably going to be more than an hour, but it's okay. I'm trying to be as detailed as possible because so that you don't fall behind. And it will also help you with your project and other homeworks, because I'm going to assign homework questions that will require you to use HSpice. Okay, I will also assign a project that you will work on using HSpice. All right, so keeping all of this in mind, I'm taking this as seriously as possible. So I'm skipping lecture 5 and heading over to lecture 6 in class. Any question? No? Okay. All right. I think I've searched something here. I want to show you. Okay, let's see. How expensive is HSpice? Let's see. Let's find out together. HSpice version 2004 is not the most cutting edge one. Starts at $20,000 for a perpetual license. Okay. Okay. I mean, the reason and this is 2004. We are using, I think we have 14 or 13, 2013 or 14. I have to double check with IT what is the most advanced node, but you can only imagine. And by the way, LTSpice, have you ever used LTSpice? You could download it from the website for free, right? So why will people pay for $20,000 for a single license? And I don't know if you know this, but perpetual licenses don't get updates, to my knowledge. Okay, they don't get updates. Whatever you get, that's it. 10 years later, you still have the same version, typically, because we have perpetual license for some software in our group, and they don't get updates. Okay, it is what it is. You have to buy a new one if you want a more advanced version. So you can only imagine how serious this software is. I'll try my best to at least expose you enough so that you could do something useful with it. But I'm hopeful that if you add it to your resume, it will get a lot of attention eventually when you go for internships and whatnot. Okay, so without further ado, let's start with the other lecture. Obviously, the more logical, the next logical step would be to go to DRAM. As I told you, SRAMs and DRAMs are like the king and queen or king and prince or whatever, however you want to put it there. They're the celebrities of memory design field, right? They're basically determining all sorts of computing devices for the last several decades. And they're still here. They're not going anywhere in the long run, at least in the short run. So what are DRAMs? We'll talk about it. I have some illustrations to show you. If you look at a simple desktop PC, you'd find that we have a solid state drive in the more advanced one, or conventional hard drive, which will be thicker and bigger and slower, of course. And there will be some cards like this in the motherboard. These are dynamic random access memory, or we often just call them RAM, but technically they are DRAM, dynamic RAM, okay, for the most part. Okay, so if you zoom into them, this is how the array looks like, and we'll gradually get into the full detail of what these are. But there will be arrays of cells. These are DRAM cells, individual DRAM cells. And if you compare them against an SSD, solid state drive, a solid state drive, which we use, like I think most of us use, if you have a Mac, it has SSD. They can have terabytes of storage now. And terabyte basically means trillion memory cells. And we'll show you where we are with DRAM. DRAM typically do not get that degree of concentration. There are reasons which we'll explain. Compare between these two celebrities that we currently use together in most cutting edge systems, DRAM and SSD. They're both there in most systems, okay? For example, in your iPhones, you have DRAMs and SSD, okay? So DRAMs, read-write speed for DRAM is typically in nanoseconds, tens of nanoseconds. Well, don't take 17 too seriously. Maybe it could be 13, it could be 21. There will be something here and there, but it's in tens of nanoseconds, as opposed to an SSD, which is in microseconds, okay? And by the way, just to show you, there is a significant difference. So if you compare that against with an analogy, if you compare SSD speed, that will be similar to this tortoise walking, and the speed of DRAM will be a Mach 3 fighter jet. Like that's how fast things are, okay, in DRAM. So that's why we have to use DRAMs, and they are closer to the processor. And they are not even remotely as fast as SRAM. SRAMs are even faster, okay? So there is no analogy with them. Okay, so if you take a DRAM hardware, it will, and break it down, there will be multiple levels. One of them will be just the exterior packaging, which has no meaning to us. Other ones will be interconnect matrix that will just help you connect different sections. And then what we are interested in is the other one, the die, where the most action will take place, and our course will only focus on that one. And just take a look at, this is how the die looks like, which we'll probably never see. You'll see the packaging. If you break it down, you'll probably have more shinier switch matrices or interconnect blocks, but you'll probably miss this one because this is not really that interesting to look at. Very dark, not too much pattern. But if you zoom into them, you will see basically it is divided into 8 die. And I'm looking at a specific example. There are many other variants, okay? Here is how you look at the DRAM die. You have 8 different bank groups, 1, 2, 3, 4, 5, 6, 7, 8. And by the way, if you zoom in, within one of these bank groups, there are 4 banks, like 1, 2, 3, 4. Am I making sense? And by the way, you probably can imagine these are all peripheral circuit that is controlling this and that side. So it's like a field, agricultural field where you are cultivating, right? These are all your fields and crops, and these are tractors that you use to basically plant or harvest. Making sense? Okay, so let's take a look at one bank, just one bank. And that one bank is made of, as you can imagine, rows and columns, okay? And these are specific numbers taken from one technology, but you just need to get yourself familiarized with the ballpark. So you have thousands of cells in a row and many tens of thousands in a column. Typically, it's like that. And there are reasons why we decided to skew it. It's not like a square, like you have 1,000 over 1,000. It's not really typically like that. And hopefully the reason will be clear to you as we move forward in the other side. Okay, so it's a more detailed picture, so when you try to address something with an address input, a portion of the address input, about 5 bits, go to selecting the bank group, and the rest, like 16 bit, goes to select the specific banks. And then within each bank, you have row decoder and column decoder, as you see, sense amplifier and column decoder. Eventually read driver and write driver, all those good stuff that I already showed you, right? This is taken from another reference. We have already gone through this high level arguments before, so I'm not getting into the detail of it. We'll have a separate lecture on these drivers later on. The same source that I took this from also showed what happens to your 31-bit address that you are dealing with in modern technologies. A portion of it goes to address the column, as you know already. Don't you know this? Did I tell you in a very, probably second or third lecture, that you have to address the row and then address the column and then get into the specific cell that you want to address. So you have row address, you have column address. And then notice, I mean, it's a very easy question, I hope. There are less number of bits in the column address than the row address. Can anybody imagine why? There are more rows, way more rows than there are columns. Okay, so that's the reason why. So notice, like at least 10,000. So this is about 10,000. This is about 70,000. So you see that difference immediately. Okay, so we decide on this algorithm level or architecture level details based on the hardware, underlying hardware. If it was the other way around, you would have changed it. And by the way, there is a portion of bits stored to just select the bank that you're getting into. So you select a bank, within the bank, you get into row and column. That's how you address them. Okay, now let's get back to this cell level view. It looks like a battery factory because that's almost similar to what you get here. So notice this cell, this is one DRAM cell. You have a transistor, you have a capacitor. We'll take a closer look at it. So this is the transistor. I don't know if it looks like it, but let me show you. This is the source, drain, or vice versa, doesn't matter. Source or drain, they're interchangeable. And you have gate, and this is a capacitor that is connected to the transistor. And that's what makes a DRAM cell. You have a transistor connected with a capacitor. Simple, as simple as that. Okay. And I told you, we use a capacitor to represent 1 and 0. When it is charged, it represents 1. When it is discharged, it represents 0. Simple way to store information. Okay. And this cell, like rightly so is called a 1T, 1C, one transistor, one capacitor. So get used to this term 1T, 1C cells. All with me? It's a very, it has a very big advantage compared to SRAM because instead of 6 transistors, you only need 1. And the capacitor shouldn't even take any extra area because it's embedded into the transistor structure. Typically, we don't connect a separate capacitor. Okay, we typically design it within the transistor structure. That's how the modern technologies work mostly. Okay, this is another closer view. I want to show you that this one doesn't show you that view. This is how the DRAM cell is connected to the rest of it. You have a word line, you have a bit line. We'll get back to it. Where is this? Yeah, I will get back to the diagram after this. Okay, give me a second. So this is the cell. This is the transistor. This is the capacitor. There you go. And as you remember, for memories, we need rows and columns. So you'll have word line running across the row. You'll have bit line running across the column, similar to SRAM. The difference here is you don't have bit line bar, just a bit line. Any problem so far? Okay, so the other end of the capacitor is connected to ground. So you have to route a line that connects this capacitor to ground, obviously. All of them will have one common end connected to ground, that's all. Okay, now, how do you read and write? Let me first explain that, and then we'll go back to this. By the way, maybe we could just get it done before, rather than leaving these loose ends. So these lines that you see, these are bit line and word line. Can anybody tell me which one is bit line, which one is word line? Let's see if you can tell me. Okay, let me show you. So word lines will be connected to the gate of the transistor. Don't you think? So all of the transistor gate, even if there is one more here, one more transistor here. They will all be connected to the word line in the row. And bit lines will be connected to the other end of the transistor, like source or drain. Typically, we call it the drain of the transistor, but doesn't matter. Like I said, it's interchangeable. Okay, so let's call it drain. So what is connected to which interconnect is connected to the gate of the transistor? Can you see that? Is it connected to the gate? That's the drain. This is the source, right? That's the bit line. And this is the word line. So now you know. And notice they are orthogonal, meaning if one of them is running horizontally, the other one will be vertical with respect to each other. Okay. And you also get a picture that they're probably not, in the same level as well. Okay. So let's move to I can finish this. So this slide only tells you that this capacitor that you're looking at, there are different kinds of capacitors that people used in the past, and they're basically continuously improving. This capacitor is extremely important because that determines how stable your stored data is. How long can the DRAM hold on to the stored data? In other words, the retention. You know why? If you have a higher capacitor, like higher capacitance, the capacitor, it can hold on to more charge. So you're safe. Remember, a capacitor will always get some random charges or lose some random charges here and there, right? You cannot just keep them like airtight all the time. So if you have significantly higher amount of charge, it's difficult to just randomly lose charge and completely forget what it was storing, or it's difficult to just get enough charge to overwhelm the system, right? So the higher the capacitance is, the better it is. But remember, typically, I don't know if you have ever worked with discrete capacitors. How many of you have worked with discrete capacitors, right? Typically, if you use the same technology, the bigger the capacitance is, the larger the capacitor will look like. There are drum-sized capacitors as well used in power systems, right? Well, the other way to avoid that would be to completely change the technology. Rather than going from electrolyte capacitance, you can go to ceramic capacitance. All on a sudden, even a tiny one will have higher capacitance, for example, right? So you can change the technology that will give you more capacitance in a smaller area. And that's exactly what the material scientists try to achieve, having more capacitance in a smaller area using different technologies. And this show you people can use MOS capacitor. MOS stand for, MOSFET. The part MOS stands for metal oxide semiconductor. 335 folks, remember we had a dedicated lecture on MOSFET capacitance, right? Because MOSFET can be used as a capacitor, basically. So that was one approach. And then stack capacitor, trench capacitor. This is kind of like a trench capacitor. You basically dig into the body of the transistor and create a capacitance there. Exactly how the name suggests. You create a trench and then make it into a capacitor. So trench capacitor or substrate, basically 3D stack capacitors are kind of more cutting edge. This is one other example. Notice. So there are different layers that you create where you can charge or store charge. So typically, the more levels you create, the higher the charge is. So that's one approach that people tried. This is another example of a trench cell where you basically dig into the transistor body and fill it with materials that will be able to store charge. Okay. And these are realistic images. These are stacked capacitor cells, like I said, stacked on top of each other. This is trench. But it doesn't matter. For the purpose of this course, we will just assume this to be a capacitor. But we should just take a moment to appreciate the amount of material science research that goes into electrical engineering as well, right? If you're a material scientist, coming up with a way to fill in this gap with a specific fancy material that could store double the charge, all on a sudden, you've improved the memory performance significantly. And you can get a patent. And all these companies will buy your patent and you get to be a millionaire, right? You see the point? So material science has a lot of effect in most of these electrical engineering aspects. Okay, so moving away from, so that's done. We don't have any other pending slides. So let's focus on this one now. Before moving on to the next slide, I want to, why is it not letting me clear this? Let's see. Okay, yeah. I am going to explain how you read and write in a DRAM cell. If you pay attention, it's probably going to be super easy to understand. Are you guys ready? Okay. Before you read and write, the moment you want to access, you activate the word line so that you know that this cell or this row will now be read. Am I making sense? Okay. By the way, let me just, let's see if we have, maybe I can draw it here right after this. maybe there is another cell right beside it, another capacitor. So both of them will get activated, by the way, when you apply the word line, right? When you assert the word line to VDD, both of them will get activated. But which one will be read? That depends on what you do with the bit line. So you see, you have the choice. Activate the row, but then activate the columns that you want, so the others don't care. Now, maybe you activate this, so this transistor is on VDD. Now you have access to the capacitor. Imagine you're trying to write something. Let's start with write, because that's super easy to explain. What do you want? You want to charge up the capacitor. Sure, apply VDD to the bit line. Apply VDD to the bit line. And the bit line will drive this capacitor, and this node voltage will go up to VDD. Say, there you go. Simple. You have charged up the capacitor. Any problem so far? There is a problem which I'm expecting somebody will point out, but if not, yes? Yeah, it will take time, no doubt. Yeah, there is always going to be a read time and write time associated with it, right? That 10 nanosecond that I showed you, there has to be a physical reason why it takes that much time. And charging up the capacitor takes time. Yes. Perfect. Thank you so much. I should give you an, I should keep some Logins chocolate or something and throw. But that's a great answer. Thank you. And I'll explain that for the folks who probably do not know. But we'll get back to it. For the sake of simplicity, let's assume that you apply VDD, you get full VDD here at this node. There you go. Simple. Okay. What's the other one? When you charge, so you are storing 1, right? VDD represents 1. But if you want to store 0, what do? You basically drive this to ground or drive this to 0. That means even if this was storing VDD, even if maybe the capacitor was charged, now it will fully discharge to ground, and eventually you get 0. Super simple write operation. Like compare that to SRAM, where there were fight between inverters, you had to size different transistors appropriately, all those problems. You don't have that here. Super easy, straightforward. There is a reason why it survived 50+ years, right? Okay. Now, how about read? Let me finish that, and then I'll answer that or address that challenge. So how do you read? You basically apply VDD to the bit line. You basically pre-charge again. When you write, you drive, but when you read, you pre-charge. Okay, there is a difference. When you pre-charge, you let it further charge up or discharge. But when you don't pre-charge, when you drive, you basically don't let it change at all. Like nobody will be able to charge it up or discharge it because you are keeping the voltage constant. Okay, so you pre-charge it to VDD over 2. Am I making sense? During read operation, you pre-charge it to VDD over 2. Here is why. Let me show you. Imagine, so you have to sense what this capacitor was storing. Was it storing 0 or was it storing VDD? You have to somehow figure it out. Okay, imagine if it was storing VDD, that means 1. What will happen then? You have a voltage difference between these two. So the capacitor within the cell will do what? It will try to charge up the bit line, right? Like, okay, it will try to charge up the bit line. It will try, yeah, the bit line voltage will go from VDD over 2 plus something, a little bit higher. And this will lose some voltage. I guess all with me? Okay, you just test a little bit, and then you shut it off. You shut off the word line. And if your bit, let's start here maybe. Let me just draw here. Imagine you started with VDD over 2. And after you were done reading, we have a separate slide which shows you that. So, but since we are here, I want to quickly show you anyways. Your bit line voltage will increase a little bit. Okay, on the other hand, if it was storing 0, then the bit line will try to charge it up a little bit. Okay, then instead of 0, this will end up being a little bit higher than 0, delta V. And the bit line will lose some voltage, VDD over 2 minus delta V. So instead of going up, it will go down. So depending on what happened to the bit line voltage, did it go up? If it went up, that means the capacitor was storing charge. So it charged up the bit line. If it went down, that means the capacitor was storing 0. Making sense? So depending on how do you sense these two differences, you add a sense amplifier again, same old story. And notice it's a single-ended bit line. So you have to connect it to a sense amplifier. And the sense amplifier will need a what? Reference voltage, okay? One other thing, the reference voltage would be VDD over 2, as you can imagine, right? If this guy is slightly above VDD over 2, you sense that. If it is slightly less than VDD over 2, you sense that. So you create a reference voltage separately, which is VDD over 2. All right. Now, there are multiple problems with this approach. Number one, okay, just to address, if you remember, NMOS transistors are not good at charging up a node. They're good at discharging. That's why in CMOS circuits, we use NMOSes and connect them to ground, and we use PMOSes and connect them to VDD so that they could charge. Remember the inverter argument? Yes, but you just need a transistor here, okay? It's true that when the NMOS tries to charge up this node, it will never be full VDD. It will be VDD minus V threshold of this of this NMOS. Just given. Okay, so if you don't like NMOS, move it, just change it to PMOS. Then you have the other issue. PMOS is not good at discharging a node. It will never be able to fully discharge, right? So one way or the other, you have an issue. So even if you use PMOS, people will ask, why PMOS? Why not NMOS, right? So they just went with NMOS because typically NMOS transistors are easier to fabricate. Okay, that's why they made a call. So remember, it's not fully VDD. It's slightly lower than VDD, but it's okay. It's not really that bad. All right. The real issue is, that's an issue, but we know that, we live with it. What is the real issue? Can anybody tell me what the real issue is? What happened during read? Yes. Yeah, that's a great question. By the way, that's a great question. Great suggestion as well. So notice what Michael said was, so imagine if your bit line was VDD over 2, that's common across everybody else, right? So when you charge up the bit line, what happens to the others? Why don't the others get affected? Remember, that's why we have separate rows. You deactivate the transistors for the other rows so they don't get affected, first of all, ideally. Okay, but there are other problems. Notice, when you try to read, not write, when you try to read, you have charge sharing with this capacitor. Either it shares charge with the bit line or the bit line shares charge with the capacitor. Either ways, it changes this node voltage, don't you think? So every time you read, you change the capacitor voltage. So next time when you read, like you are taking away some voltage. Imagine it was storing 0.9 volt, and that's your VDD, say 0.9 volt. I'm assuming this is an idealistic scenario, okay? After you read the first time, it becomes 0.8. If you read it again, 0.7, and so on. So you basically take away voltage from this one. So it makes it challenging to, and at some point it will fail. It will be misclassified as 0, right? So you don't want to let that happen. So the thing is, every time you read, you have to, either you have to write back, or you have to selectively, we call it, there are two things. Every time you read, you write back. So I've just read that it was storing 1. So I do a write operation right after this and write it back. That's one option. The other option is, every time we read a row, we block off that row. I'm not going to read the row next time, right after the first read. So I'll have to, what they call it is refresh. So basically they refresh the entire row. Here is why. Still paying attention? Okay. Remember, even if you don't read or write, let me tell you what, this is a more recent problem over the last 10, 15 years. People didn't really suffer that much with it, but now they're doing it. So even if it is storing VDD, you are not reading or writing, this VDD will gradually go down. Why? Thank you. Yes, that's why you spend so much time talking about leakage. It's so crucial that, even if you don't do anything, this transistor is still leaking current, and that current will basically let this capacitor discharge continuously. And it is so bad that every microsecond, you have to refresh, because it will lose so much charge. Because it doesn't anyways have that much charge, honestly. The capacitors are tiny. Oh, I forgot to sorry, that was the other reason why I had this slide. Notice this is 360 nanometer, 32 nanometer, 60, it's in few tens of nanometers. It's really tiny. And the capacitors that you have, that you can hold in your hand, the microfarads or nano, you see that? They're big. You could see them. You could hold them in your, and these are like smaller than virus, bacteria, something like that, right? So you see, the problem is you don't have much charge to live with anyways. And because of leakage, you are losing charges continuously. So you have to do what? You have to continuously write. So we call them refresh operation. So refresh is nothing but a read and write. So you read and you write, because otherwise, how will you know what to write if you don't read? So you read a row, and whatever you read, you write back. I read one, I will write one back exactly at that location. Isn't that a waste of resources if you think like you're unnecessarily reading and writing from the memory cell continuously? Okay. Now, I hope as an engineer, you see the resource challenge there, right? If you have a battery with your laptop, your iPhone, you're spending the energy to continuously refresh rows, without any other reason. Maybe you don't need it, but you have to make sure that the data is integrated. So that's one of the reason. I mean, I'm going to go back quickly and show you one thing. Why SSDs, not this slide, they're allowed to have terabytes, really high storage, but not DRAMs, because the more you store, the more you have to refresh, and that will be a nightmare for your energy density. So even if we can accommodate more storage, we don't, because you see the point. And also, we haven't been to the slide yet, but I still want to mention that here. One of the reasons why you have that many rows versus column is because you refresh in rows. Okay, so after you read a row, you just set it aside, you just reserve it. It's not available anymore, right? You use the other row. So when you are executing algorithms, you want to make sure there are many rows available. So just get to the next row and work with it. Get to the next row, work with it. Okay. Meanwhile, you'll finish refreshing. Otherwise, the overall execution will be super slow, because the processor will wait. Okay, I'll let you refresh first, and then I'll work. But it takes some time. I'll show you some numbers to refresh. I'll show you that when we get to the refresh discussion. It's probably there. I'll show you in a second. But it takes some time to refresh. Okay. So while you are refreshing, you don't want to just wait there. So you have many other rows as redundant rows that you could use. And basically, the DRAM refreshes row by row. Like you start from first row and finish refreshing everything else, and then go back to the first row again. So there is a refresh cycle that is continuous. That is known as the biggest challenge with DRAM. Okay. So now, do you understand how read and write works for DRAM? Is it not easy enough? Okay, we have already seen word line, bit line, and gate and transistors and whatnot. This is the slide that I told you that I will show you. Let's try to make sense of it together. This is your word line. You activate the word line during write one. Notice that. Okay. So we are trying to write one. This is activated now. I'm going to use a different color. What happens to bit line? Notice bit line is charged to VDD because you want to write one. Right? What I just told you, VDD. So apparently, what happens to this storage node voltage? No, maybe it was 0 before. Now it will be charged up, but it will not be charged up to VDD. It will be VDD minus V threshold, as I told you. Okay, doesn't matter. It will be charged high. Okay, then when you read one, what do you do? Notice the bit line is no longer VDD. It's VDD over 2 now. So before you do the read operation, you have to precondition your bit line. For write, it's VDD and 0. For read, it's VDD over 2. So you precondition your bit line to VDD over 2. So you don't turn on your word line right away. Like, okay, you don't just, keep reading and writing. After you finish writing, you have to shut off your word line and then precondition your bit line. And then you can activate your word line again so that you have the right environment set up for reading. And notice during reading, since it was storing 1, your bit line voltage is going up. Does that make sense to you, folks? Is it not? So this was VDD over 2. And when you activate the word line, this bit line voltage started going up. And notice what happens to the other one. This storage node voltage, it goes down at the same time, right? Because it gave the charge to the bit line. Yes. Yeah, so basically, whatever you are increasing here, so this charge goes to the bit line directly. And I didn't mention that before, but remember, if you see my SRAM slides as well, there will always be a capacitor connected to the bit line. Any bit line, even word line has it, but typically bit lines have more capacitance. Okay, there are reasons, but did I tell you that even if you draw an interconnect line, it's as if you have a huge capacitor connected? It's free. You don't connect a capacitor there. It's basically the bit line capacitance. Okay, did I talk about it in the class? If you don't remember, okay. So basically, this is a capacitor. This is another capacitor. When this capacitor loses charge, the other one gains it. That's where the charge goes. Okay, there are some leakages here and there, but most of it goes to the bit line. Yes. Yes. Basically, that's lost to ground. Okay, that's lost to ground. So you have driver ICs that changes the voltages of the bit line, and they basically completely obliterate that additional voltage. So it's a lost energy for sure. Any other question? Okay, so you see that when you write one, your bit line voltage increases, and if you see read 0, your bit line voltage will decrease, quite opposite to read 1, right? And basically just go through this timeline, this transient waveform, and see how write 1, read 1, write 0, read 0 works, which I already explained individually. Okay, so what you need take home from this slide is that we use the term quite often in memory design. DRAM, at least 1P, 1C DRAM, this design has a destructive read, meaning when you read, you basically destroy the stored data to some extent, but it's essentially destroying it. Okay? And then it needs refresh for sure, as you can see, and it has an incomplete swing. What does that mean? Notice, instead of going from 0 to VDD, you are going in the storage node 0 to VDD minus V threshold. Okay, that's the problem. By the way, in SRAM, our storage node was always 0 to VDD. Remember? Do you remember that? There was no issue whatsoever in SRAM. You always went from 0 to VDD. But for DRAM, you go from 0 to VDD minus V threshold. That's the challenge. You know why that's the challenge? Imagine, let's take some numbers here. Imagine your threshold voltage is 0.2 volt. And your VDD is 1 volt. You are losing 20% of voltage for nothing. So you only get 0.8 volt here, max. But now everyone is trying to reduce the supply voltage. Nobody's trying to increase it, by the way. Okay. So when your supply voltage becomes 0.5 volt, you're only getting 0.3 volt here. So you're basically operating at the edge. And there are reasons why we cannot reduce threshold voltage anymore. Okay. And I'm not getting into the, don't get me started on that. Like that's related to 2 years of my PhD research. So it's extremely challenging to reduce threshold voltage below a certain level, unless you come up with ways to beat the fundamental Boltzmann limit. I think I hinted at it in one of the lectures, right? That's why people are so crazy. There are millions of dollars of research funding everywhere to find transistors that will allow you to beat the Boltzmann limit. So without beating that limit, you cannot reduce the threshold voltage further. So you're kind of stuck. So that's where this incomplete swing becomes a challenge. You are anyways losing a portion of the VDD, which is bad. Okay. All right. So this basically tells you the exact same story, but adds the argument of charge sharing between these two. Basically, what is the final charge of this capacitor? Whatever charge this capacitor loses, the other one gains, and vice versa. So the same slide, except that we add some argument about charge sharing. Okay. All right. So I just want to finish this slide at least because it does the exact same job. Notice, when you pre-charge the bit line, we see what happens to the bit line during read and write operation. During read operation, it could either go up or go down. So you create delta V. And then after you're done reading, notice that's where you activate your sense amplifier. By the way, if you gave it you pointed it out that it will take some time to share the charge, right? Okay. How long will it take to completely charge it up to VDD or completely discharge it to VDD over to whatever, right? How long will it take to create more difference? More time. So question is, okay, if I waited more, it would have been here. It would have been easier to sense, don't you think? But where do we draw the line? Where do we stop? That depends on the specification of the sense amplifier. That's where the lecture with sense amplifiers will be so critical. If you come up with a fancy sense amplifier that has high resolution, it could sense really small difference. Otherwise, you have to wait more. If you wait more, what are you losing? You're losing read time. Instead of 10 nanosecond, it will be 50 nanosecond, which you don't want, okay? And remember, 50 nanosecond reading just one bit. So it's crazy, right? So that's what this slide tells you. That's when you activate the sense amplifier. And after that, you don't care. You just take it back to VDD or 0. Right? Am I making sense? All right. So that's the slide where we will stop today. And in the next class, we'll resume from this one.